So today's class basically will be talking will be introducing machine learning from the perspective of computer vision especially. So what till now basically we have actually covered topics in computer vision which were at low level processing and at mid level processing. So in low level processing uh, we had basically discussed very simple image manipulations from pixel level to to transforming images spatially, geometrically. We have seen the methods for image enhancements, restoration, noise removal, etc. We had seen edge detections, which are kind of low-level features from images, and we also discussed about different color models to extract color information and so on. In mid-level topics that we have discussed, after the first sessional, we discussed invariant features detections like Harris and Swift. We discussed topics related to model fitting and feature matching. So we discussed methods like Huff transform and Landsat, so on, and they had applications for panorama, stitching panorama, and so on. We moved on to image segmentation, which is kind of we can say it can be also categorized as a high-level topic. So we discuss simple clustering techniques and other methods for segmenting out regions. And we discuss moving object detection using background subtraction and tracking. And we ended up last class, we discussed a simple methods of representation and description descriptors for simple binary regions and shapes in an image. So we have already covered a lot of topics, but till now we have actually not tried to address a very fundamental problem at a higher level, taking an image and extracting some meaning out of it, some semantics in that image, what that image contains all about, what kind of an object it is, where it is, and all that thing, some kind of an understanding about an image in an automatic fashion. And we actually will see whatever we have done. Actually, for example, we extracted features. Those things actually get used for high-level image, high-level vision. So now we are going to move on making some predictions on an images. So taking an image, doing some low-level or mid-level processing, and then using some, we'll see some methods and algorithms by which we can make some prediction about the images. There are different types of predictions that we can do. We can have a classification task, we can have a detection task, and so on. For doing this thing in two categories. So people have in the old school, or in fact in very early research, people actually mostly use some hard-coded rules and some models which were manually identified and assumed to be true. And using those simple heuristics and rules, we could actually write a function and hard code those rules, and given an input image, we can actually return a class label. More recently, especially with the more statistics and machine learning picking up, the other approach has become more prominent, where you try to learn the algorithm from the data itself. So you given a lot of images. Once you have data set of images and their corresponding values which you want to predict, we can try to learn those rules. We can try to learn those algorithms automatically from the data itself. Early computer vision, basically, as I said, they basically used try to basically use our human understanding about the world and how vision functions, and they try to use simple mathematical models to basically represent our description of objects in an image. So these are very simple paper from where the objects were tried to be recognized using components. So people basically use models of simple components of different shapes and so on, and by combining those components in some hard-coded way, in some using some particular patterns, you could actually learn more complicated shapes. This is another example, an early paper of face detection of face on an image. So there also, as you can see, the researchers basically came up with some kind of a model of a face. It should have components like eyes and nose, and basically on the ears there should be edges on the left and right. And then these components, so these parts are connected by some elastic spring kind of a thing. So the distance between these parts, basically, that means it has it can actually go from some finite range. So there is some relaxation possible there, because different people have different structures of shape. So these different parts, the overall arrangement pattern can be modeled by this, and the distances from this can have some range. And these methods actually worked on very restrictive set of images and very simple scenarios. And we had actually seen when we in the first class, when we introduced this course, we showed many examples of real world challenges in recognition. There are intra-class variations. There are so many variations within each class, and there is a background clutter there. There are deformation possible in shapes and objects, and so on. So there are a number of challenges, and really coming up with a mathematical model or to basically be able to handle all those variations is a very infeasible thing. You cannot actually come up with a well-defined mathematical model which can account for, or which can explain all those variations that we find in a real life scenario. So more recently, a data-driven approach has become popular. More recently, I think more than 2 decades or 3 decades, you can say. Machine learning has been being used in computer vision. So the general idea here is basically we need a data set of images, and the things that you're trying to predict, either class labels or whatever values that you want to predict. And then you use some machine learning algorithm to basically train a classifier or predictor on that data set. And then you use those. So an example is shown here of, you have some data sets. This is an example of image classification. So we have images of different objects in them, and they are basically given labels according to the object categorization. So you use this training set of data. So basically, you try to use then trained classifier on a test image. So there has been some part of the data set would be used as a test, used for testing purpose, and some part will be used for training purpose. So you take training images and the training labels to train our model. You will have some method, some algorithm to do that, and this will return a trained model, which you can use for prediction purpose. So there, the predictor will basically take the trained model and the test images and will return the prediction score, the label of one. In this case, for a classification task, it will return just the label of the class. So this looks an abstract thing. Let us go into more detail what basically this data-driven approach means. We are basically going to talk about more data-driven approach only, because that is the method which is popular and which actually gives meaningful result. So here I'm basically now the next few slides are going to be some animated slides. It was so nice. I got it from internet, so I could not resist stealing them and putting it here. It basically describes the basic machine learning approach in a very high level thing. So you can think of machine learning basically as a mathematical model, as a mathematical function, where you basically take the input values in your training data set. Those your input values basically we can call them as features or some numerical values. And you are basically, this mathematical function will try to will predict a value, which can be a continuous value, or it can be a class label, or even a class probability. So depending on what kind of task, what kind of machine learning tool you have used, generally there are two sets of machine learning methods. One is called regression and the other is called classifier. In regression, basically we predict a continuous value, whereas in a classification task, you basically predict just the label of the class, or maybe the probability, with what probability you think that this object belongs to a particular class label. So a canonical example in machine learning is, in almost all books you will start find this is a hello world example of machine learning. So basically, for example, let us say you want to predict the class of iris flower. So it's a particular flower. Now to predict this class, which species of the iris flower it actually belongs to, you can actually use some important features, which are some characteristic information that you can extract from this data. So for example, you can use the measurement, the length and the breadth or height of the petals as well as the sepals of this flower. And these will be some numerical values. And your output value y will basically a class label, whether it belongs to Setosa species or versicolor or virginica. Now you can give them some discrete labels like 0, 1, 2, and let the function learn, take this as input and output either the label itself or maybe a set of probabilities for each class. So for example, it can, in this case, it is predicting for this particular input data, it is predicting 0 probability for the first and the third class, and 100% probability for the second class. So basically, in this case, that means the predicted species of the flower is the versicolor flower species. How does the function is learned? So basically, you need a data set for this, which we have collected beforehand as a ground truth. So you will have, the data set will have basically the numerical values of the feature values, and in addition, they will have labels which would be manually given to each sample, each data point. So in this previous example, we have 3 labels, 0, 1, and 2. So now you need to learn this function. So your input is now has at least 4 different values. So it will be a multi-dimensional space. Now you need to learn this function. So you will basically use a part of this data set for training purpose. So our machine learning algorithm will try to use that set of data points to basically automatically learn the classifier, which can be in form of the boundaries between those 2-3 classes. Those boundaries can be represented by linear boundaries or some, we'll see later on what are the methods for doing. So you can use some functions like logistic regression, linear classifier, whatever, to basically learn how in this multi-dimensional space, how to discriminate, how to discriminate between these 3 set of data points in this. Now you can use the remaining withheld set of data, which you can call it as a validation set, and again see what is the predicted value on the validation set. Now you can actually use the result of the predicted value on the validation set and match them against the actual ground truth. And you can actually tabulate this kind of a data. So this is normally called confusion matrix. Get you familiarized with the terms that get used very frequently in machine learning, because those terms will get frequently used when we discuss going to discuss the higher topics. So this is kind of a confusion matrix where you have on one side you have predicted value, and on the other side you have a actual label. So wherever the predicted value and actual labels match, generally these are the diagonal values. So whenever the two matches, this is the number of true matches, and these are false matches basically. So ideally, you would like to have very high value in this diagonal and low values on the other side of all other places in the matrix. So based on this confusion matrix, you can calculate the overall accuracy and precision, and so on. There are other parameters, and that will help us to know how well our model has got trained and how well it is generalizing in an unseen scenario. So the validation set was probably the one which it did not see during the training time. So if it performs well on the validation set, then that means it is generalizing. Even if you give a sample which the algorithm has not seen before, it will still be able to predict it to a good, reasonable level of accuracy. So this was about traditional image machine learning, but in images, basically, now we can actually take a photograph of the flower itself, which will be basically a collection of pixel values, which are again some numerical values. So instead of actually extracting those features like the length and the breadth of petals and sepals, you can actually even use the raw pixel values of your images itself as your data points. So you can actually put them together in our training set, concatenate all the pixel values and along with the labels. So the features now basically can be even just the raw pixel values, and you can have the labels as per that, and then again do the same process. You divide it into training and validation set and learn the function. And when you're happy with the function, you take a new image, apply the function on that, and it will give you the class probability of the labels of the predicted thing. Okay, so we have basically covered a very broad recognition framework, broad general framework using machine learning. We are going to delve in more detail into it. So, but before that, it was found very soon that methods that use this type of training data approach, they quickly outperform modeling approaches, the heuristic-based approach or hard-coded rules. So from 1990 onwards, people started using finding this thing, and from then onwards, machine learning has become actually a core part of high-level computer vision task. So mostly you won't find any algorithm, any methods which doesn't use some kind of machine learning in a high-level computer vision task. And nearly every machine learning algorithm has been used in one way or another in computer vision. In fact, there are n number of machine learning algorithms, and almost everyone has been experimented to see which one performs better in computer vision. And in fact, computer vision actually is a rich source for machine learning people. Machine learning people frequently use computer vision problems. So I don't intend to go too much deep into machine learning things, but we still need to do a crash course on this. So I do intend to cover most of the important machine learning approaches that get frequently used in computer vision to a sufficient depth, so that you know actually the concept behind them, not just the superficial high-level understanding. Okay, so what is machine learning basically? It borrows concepts most from statistics and so on, and uses algorithms or techniques to basically approximate our function wiser to fx given a training set of input values and predicted values. Using statistical methods and all that, you try to basically learn this function, and how this function is learned, you try to basically optimize some optimization function, which is kind of a loss function. And you can broadly, there are 2 or 3 types of machine learning approaches. One is called supervised learning, where basically you have lots of labeled examples in your data set. So you already the ground truth is already made available by manual labeling or whatever, And then basically you use those to learn the function, and then given an input to a function, you try to predict the output. There is a semi-supervised method also where you have a lot of examples, a lot of training data, but the number of labeled examples are far less or lesser than the total number of data sets. So you could actually, because manual labeling is quite expensive, and you may not be able to label every sample. So, but if you are able to label some of them, then there are a set of techniques which comes under semi-supervised learning, which can work with that. And there is a third class of method which is called unsupervised learning, where you don't go for manual labeling. You try to use algorithms which automatically tries to group the unlabeled data by finding similarity and differences between them. So basically, we have already seen unsupervised learning in action earlier when we were discussing automatic segmentation. So we use basically k-means clustering methods and so on. Mean shift and so on. So we saw how basically k-means clustering actually works. So you don't need any manual labels a priori. You just need the data points, and based on the distribution in the n-dimensional space, it tries to cluster them into different groups, and based on that, it comes up with a label to that. And we had seen how k-means clustering performs for segmentation tasks earlier. So I'm not going to go, we will not review it again. What we are going to more focus on supervised learning, because that is what gets most frequently used in high-level machine learning tasks. And in supervised learning, basically, the core of the problem is to estimate this function f. Given a set of independent variable x fits our feature data, you want to compute a function which can predict the dependent variable y or label of the class or whatever. So you have some data points and you want to learn this function. So one simple for example, in this case, if you have a distribution like this, you have just one independent variable x. One possible function can be a straight line which explains this data. But as we have talked very often, that in real life we won't get that kind of a clean data. Even if the real function is actually a straight line, the data points will have some noise, some Gaussian noise, and so on. And why noise? We have already talked about it earlier. I'll repeat it just one more time, because there is some randomness when you're capturing the images, depending on the distribution of photons hitting the sensors and some electrical disturbance and so on. You can have some randomness in the data points in the image itself. There may be errors during human labeling of the data. There may be some occlusion or something. There may be variables outside of the models. So you may be assuming some model, but there may be some things which cannot be explained by the model. So for example, if there is an occlusion happening, or if some other things that has happened which your model cannot take into account. So those are like real things. Those are not really noise, but those are like unknown variables. You cannot actually, your model is not capable enough to handle those things. So, but they will appear for your machine learning algorithm, they will appear like noise to the noise in the data. So then what is the solution? Do we need to go for a very complex function like this, which tries to explain away each and every point in the distribution space? So this is an example of a more complex function, higher dimensional polynomial, or maybe n-dimensional thing. So so now you have a problem now. You have a choice whether to go for a more simpler model, simpler function, or go for a more complex function which tries to explain each and every point. Because as I said, data may be noise, or it may not be noise. It may be an actual point which we don't know, which can be due to some things. So this problem that we just talked about is popularly known in machine learning discussion or machine learning literatures as the popular famous bias variance trade-off problem. You have two things which you need to basically you have to be sensitive to. One is called bias. The bias basically is a result of making assumptions on your model. So making assumptions on your data. So for example, you made an assumption that the data is linear. So you try to fit a linear model to your data, but your actual data may not be linear. So you are assuming a very simple linear model. So there will be errors in fitting this data points on to this simple function. So actual function may be a quadratic. For example, in this case, instead of using a simple linear function, you can actually go for a quadratic function, which is not much more complex. A quadratic function is also computable easily. It's not so complex function, but it actually explains away each and every point in this case. So having a very high, so this model, if for example linear, if you're using a very simple model, it will be biased towards that model. So it will not take into account it may not use a lot of useful information in your data to learn a good function. So it will be more biased to the linear model or whatever that you have made an assumption. The other thing is other problem in learning this function is variance. So this variance can be explained as the sensitivity of the algorithm to noise. So generally more complex functions or more complex algorithms will be more sensitive to noise. So what basically this means, what I'm going to explain here, let us say we have these points. Let us say we have two sets of, let us subsample into two sets. One set is this purple dots and one set of samples is this red dots. So now let us say if your training data was just comprising of these purple dots and you try to fit a more complex function which tries to explain each and every point, you would get this kind of a complex function f. However, if you had a slightly different subset of training sample like these red data points, you will learn an altogether function which is shown here, f dash. Now this f and f dash will be a totally different function. So that means though your algorithm is having a very high variance, it is varying very much as your data is varying. So if you have a different set of data point or slightly different set of data points, the function which will be learned will be totally different than what it will be done otherwise. So it will have a very high variance. So this high variance, the problem with this high variance is that it will hurt your generalization capability of your function. This is also called overfitting. Later on, we'll talk about it. Basically your function is overfitting to your problem or to your data points. So when you are given a new set of new data points, it can predict totally meaningless output to that. It will not generalize well for another set of problems or another set of data sets or another set new unseen test sample. So as we have based on our discussion, now we know bias and variance are two opposite things. If you try to go for a more simpler method, you will be ending up biasing your algorithms towards a simple model, and you will not be learning the exact patterns in your data. Whereas if you go for a more complex algorithm, it will have low generalization capability. It will have a very high variance. So you need some kind of a sense, you find a sensitive trade-off between these two things. And that is actually one of the difficult problem in machine learning. There is no magic solution. And we'll come to it again later on when we talk in more details. So let us start with some simple methods of techniques for machine for learning this function. So one of the simplest method is called linear regression. So what this linear regression basically does is basically it tries to fit a fit a line, assuming the model is linear model. It tries to fit a line on the distribution set, and then tries to learn the parameters of the line A and B in this case. We have already talked about it, so I'm not going to talk it again. We know we have tried when we were discussing model fitting. We had seen how to find the best fit line and all that. So we basically do some kind of find a loss function. Basically, in this case, we try to minimize the square. So we try to minimize sum of squared differences error. So your function that you're trying to, so if this is a predicted value and this is the actual value, you try to find the actual the squared error between the two, and try to minimize this this function. And while trying to minimize this function, the one which gives the values of A and B, which gives that minimum loss function, will be the actual line which fits on this data. And in this case, for example, you can simply do a differentiation, find the derivative, and equate it to 0. And you can, as we had seen earlier, it basically ends up giving a linear system of equations. You can solve using simple linear algebra to find out these A and B values. Well, now this model, as we have already talked, this is an example of a high bias. We are assuming linear things, and will have a very low variance. So benefit with this model, it has a closed form solution. To find this A and B value, you have a well-defined expression, mathematical expression. You can just straight away use this. From the previous thing, by putting derivative to equal to 0, you will get a well-defined formula for this, and you can use that formula to find the A and B value. So it can be done very fast. And also, when you have to predict, when a new data comes, when you have to predict its value, it's just one multiplication and one addition. So it's very fast. You will predict some continuous value for a new unseen data point. You will be able to predict its output value very quickly. It has weaknesses. It will not be very powerful. It will not be able to fit more data like coordinate data and all that. So more interesting data will not be able to fit on this. One thing that again we will come again and again. So an aside point here. So while we are finding our loss function, which we are trying to minimize or maximize, our loss function or optimization function can be a convex function or a non-convex function. If it is a convex function, how to know whether it is a convex function? If you connect 2 points on that function, the points on the line will always will be always about to the actual function. Whereas in a non-convex function, concave function, it won't be so. So if you have a convex function is very good in this. If your loss function is convex, it is very, very advantageous, because in that case you will have just one global minima. So there will be just one global minima. So there is no problem with local minima here. So you can basically find out the derivative and put it to 0 and solve for the parameters. So it will be easy to find the parameters. Will be finding very easy. But if you have a non-convex function, loss function, then you cannot do that. You cannot just find a derivative and put it to 0, because there are, in this region, if you are trying to do it, you will get a local minima here. In this region, you get a local minima here, whereas the global minima is somewhere around there. So there is no easy way to find global or local optimum value. So you'll have to go for some methods to optimize that. We'll see later on gradient descent and all that methods to find an optimum minima value for non-convex function. The other method which is quite opposite to linear regression is nearest neighbor method. So in nearest neighbor method, basically what your function is nothing but you find, you have a new data point, you find the nearest point in your training set, which is nearest to the new data point, and just assign the value of that data point to as a predicted value. So for example, if you're finding a new point somewhere here, find which is the nearest point in your training data set. For point here, and the nearest point will be here. For a point here, and the nearest point will be somewhere here, and you end up predicting the same value of that point as your output. So you get some kind of a step function for this thing. As the function that gets learned is this kind of a complex function. So as we had seen earlier, this is going to have a very high variance. If you have a different set of training data samples in the things, your function will be totally different. Whereas it has very low bias, it has no assumption about the data. Benefits, again, it is very easy to implement. You don't have to do any learning or finding any parameters. You just and it's very easy to understand. At the test time, you just find the nearest point to that feature vector and just predict its things. And what is interesting, it can sometimes be very powerful also, especially if you have lots of training data. If you have lots of training data, invariably you will end up finding a point which is very close to that, and most probably you may have the similar values for the predicted value may actually match with the actual value. There are disadvantages with this. It is hard to scale because you have to, first of all, you have to keep in memory all the training data points in your memory during the test time, and then you need to match the nearest. Finding the nearest neighbor itself can be a very computational expensive task if you have lots and lots of samples in your training data sets. So it will be hard to scale if you have millions of data points in your data set. And again, as we had seen, it will be prone to overfitting. If you have some data points are noisy points, then you will end up in a problem zone. So these were some examples of regression. We were trying to predict a continuous value given a new data point. You were predicting some continuous value output variable. As I said earlier, there is another set of tasks which in machine learning, which is called a classification task. It is slightly different than a regression task in the sense in classification task, it's a discrete value that you want to predict. You don't want to predict output a continuous value. You want to predict a discrete value. A discrete value it can be associated with a class. You have a class of labels and you want to predict the labels of class labels or something like that. An example is shown here. For example, here, this is an example of a binary classification. You have some data points of a patient, some data set of patients' characteristics, their symptoms. It is relevant in today's current context. So if you have some symptoms, some data set, data points regarding various symptoms related to flu, and then you want to basically diagnose, you want to basically find output whether the patient has the flu or not flu. So it's a binary class problem. It's a 0, and you can give a label 0 or 1. Whether if the person has flu, you give the label 1, otherwise 0. So now this data set doesn't always has a numerical value. It can have a float value, it can have integer values, it can have a continuous value, it can have discrete values. For example, sore throat, whether yes or no, runny nose, yes or no. So you can convert them into numeric value by giving some kind of encoding. If there are only 2 classes, you can again give them 0, 1 values. If there are multiple things, you give some kind of a discrete encoding to that, and you can convert everything into some numerical values and use that to learn our classifier. In this case, for example, one very simple approach which is used for doing binary classification or classification tasks is method of partitioning. So, for example, in this data set, if you see this parameter temperature, and you see people having flu, they were having almost high temperature, 101, 100, 99.8, and one here 99.9 was having not flu. So most of them having a temperature greater than 99.5, you can say that's a clear indication that a person has flu, except for some noisy case here. So you can basically use just this criteria, seeing the temperature value, seeing whether it is greater than 99.5, so thresholding, and deciding on the predicted label. So how can you do this? What methods basically find out which parameter to use and what should be the partition point and so on. There are methods in that. One of the methods which is used in machine learning is called decision trees. Which is very popular model in machine learning, because first of all, it is a very simple model and it is very interpretable. It is very easy to explain. The model is very easy to interpret even by a non-machine learning expert. So for example, in this case scenario, let us say, depending on whether the weather is sunny or rainy, you have two choices. If it is rainy, you don't want to go outside, you want to be in your room or lab and do your work. If it is sunny, you want to go outside, and while going outside, you may want to do different tasks, depending on the temperature. If the temperature is very high, you may want to go towards the beach and relax there, or if you have less temperature, you may want to go for a more intense exercise like hiking and so on. So it is very easy to understand how, and it has good application, especially in medicine. For example, to a doctor, for example, as in the previous example of the sore throat and flu things, if you construct a decision tree like this, a doctor will be more comfortable in using the prediction of this model, because it can go through this, what is the model that has been learned, and it can make a sense that it is actually making a sense to me from his own domain knowledge. And he will be more confident in using the output of this model, because it is more explainable and more interpretable. Whereas some other methods like neural network and other methods where you just give in a bunch of numerical value and basically the algorithm blurts out some other numerical value and say, okay, now it basically predicts, so with 90% confidence, it says it belongs to class 0 or it should go to beach. Never mind how it learned, what was the method it used to arrive at that conclusion, and so on. So those are more black box methods, and those cannot be easily explained by them. So a person may not be very confident in using those output of those models, because they may give a totally different output sometimes, which can be very wrong in some, especially for crucial applications like treatment and all that. These types of simple interpretable model are more popular than more complex methods like neural networks and so on. Let's see how much time there is. So for the previous example of this, we have multi-levels. It can be basically seen multi-level partitioning. So we have one level partitioning at this node, another level partitioning at this node on different parameters. So if you see on higher dimensional space, you have basically partitioned your space in this way. So depending on now, basically, so you had data points, and from those data points, basically you learn this partition. And now, if depending on where your new data sample points fall into which space, you will predict that as an output. So if your sample point is here, you will predict that it's a rainy situation, so you should be in a computer lab. If you find on this, you should go to beach, and so on. Sometimes there may be noise in the data, as we said. The data may not be so clear, it should not have a clear boundary. So this point ideally should have been here, but it goes here. These red points come here, and these green points come here. So there will be some noise in the along the boundaries. So you may not want to do this hard assignment. Instead of doing this hard assignment, you may go for some probabilistic assignment. So for example, if you so depending on the points where there is, whether it is near the boundary and what was the boundary, you can come up with some score, some confidence score. And okay, you say, okay, 90% I would say you would be inside, and 5% you would be outside, and so on. So this kind of methods are also there. You can actually go for soft assignments using maybe some fuzzy logic or whatever along with your decision tree. So one method, one very popular thing which is actually kind of based on this kind of a partitioning strategy. It's not exactly partitioning strategy, but I wanted to cover this particular algorithm because it's such a popular algorithm and it gets frequently cited in computer vision literature, because it was one of the very earlier successful example of computer vision techniques. So it is popularly known as Boyle-Jones phase detector, because the people who invented this were Boyle and Jones. Basically, the good thing at that time, this method, they wanted basically a very fast method which could actually run on a camera or a cell phone on some kind of an embedded device. So the method should not be very computationally expensive or memory expensive, and at the same time it should be very accurate. So actually, if we see most of our cameras that we used, either cell phone camera or your handy cam or whatever digital camera, even 5 years back or 10 years back, you can see that they had this capability to detect faces in those things. And the algorithm, guess what algorithm they use? Actually, the inbuilt algorithm in those cameras that is running is this Boyle-Jones face detector, because this actually worked quite accurately with very less time in a very efficient manner. So I just want to discuss this in this context here. It's kind of a digression from the main topic, but I doubt whether we'll again revisit this again, so I don't want to skip it. So I'm going to discuss it here and maybe end today's class at this point itself. So the idea here was there were 2 or 3 quite distinct ideas which stand out at that time. Those were quite innovative ideas. First of all, they used very simple features and classifiers to do this task. The features that they used, they were called Haar features, but they basically, you can see, understand them kind of as a rectangular filters with white and black regions. And these filters basically were used to basically understand some brightness pattern in the image. So how these filters would, how the filters would actually be calculated? The calculation methods was very simple. For example, in this case, you sum up the pixel in black region and sum of the pixel in white region and take a difference of 2, or vice versa. I don't know whether it's white minus black region or whatever. But the idea is basically you sum up all the pixels in one part of the region and sum of the pixels in another part of the region and take a difference of the 2. In this case, now this black and white patterns, they came up with multiple black and white patterns, like some simple patterns are shown here. And basically they would run this filters on the entire image and calculate the response at every location. Normally they would resize the so they would calculate these filters on a 24 by 24 size window. The base size was 24 by 24 window. What basically it means, we'll explain later. But first of all, why these simple features work for faces? Why they are good for face detection? For example, let us take these 2 simple Haar features. Now, as you can see, this type of feature, this type of filter is very useful for detecting eyes regions. Because what you see on the eye regions, you will find these are more black pixels, and after this, on the cheek part, there will be more lighter regions, because eyes are inside and there is always a shadow of eyebrows and other parts of the sockets of the eyes on the eyes region. So normally your eye regions are generally more darker than your forehead and your cheek part. So accordingly, these type of filters, either black hair or white hair or black hair or white filter, they will give a high response on this region. Similarly, this kind of filter will give a high response on the bridge of the nose, because on the bridge of the nose, generally again will be a brighter region as compared to the left and the righter side of these things, which will be the left and right eyes. So these will be more dark, and the nose bridge will be more white. So this type of filter will actually give a high response for those regions. And similarly, other regions for mouth and nose will be. So they use actually a bunch of these different types of filters to calculate responses on the features. But now, if you use all these features and do a calculation, will it not be expensive? The thing is, no, it won't be expensive, because they use a concept called integral image, which can actually be used to compute these sums over region in very fast manner. What is this integral image? Let us try to understand this. And so before calculating these filter responses, they basically took this image and they calculated an integral image of this. What is an integral image? The integral image says basically at any point x comma y, you basically, the value at x comma y will be the sum of all the pixels before it and towards the left of it. So that means all the pixels in this region, the sum of all the pixels in this region will be accumulated, and this location will be replaced by the sum of all these pixels in above and towards the left of x comma y. So if you do this for all the locations, you get a new image which is called an integral image. Now, using that integral image, it is very easy to find the sum of any region, sum of pixels in any region, with just few plus and minuses. How? So let us say we are interested in finding the sum of pixel regions in this rectangular ABCD. So you have an integral image. So at every location, we have stored the sum of all the values on the before it and towards the left of it. And we are interested in finding the sum of values in this rectangle ABCD. So you can calculate this sum by two subtraction and one addition of the integral image values. Now, can you understand this equation, how this equation is coming up? So if you can't understand, let me explain it here. So we'll first take the value at A. So value at A will be the sum of all the shaded region. Now I'll subtract the value of B, which will remove all these parts from all the pixels in this region. Then I'll subtract the value of C, which will remove all the sum of the pixels on this region. Now we have subtracted these pixels two times, because once while subtracting B and once while subtracting C. So what we'll do, we'll add the value at D to regain this, so that this 2 times subtraction is taken care of. So once we do this, we'll be only left with the pixel value, the sum of the pixels in these locations. So using this integral image, now you can calculate these Haar filter responses very easily for different, because what we are trying to calculate the sum of pixels in black and white portions, which are basically rectangular portions, and it's very easy to do that calculations in real time. Okay, so that was about feature computation. Now how about classification? How does it classifies whether there is a face or not? Now for classify purpose, they use a technique which is called boosting, and which is basically an extension of partitioning method that we were discussing earlier, decision partition or decision tree method, which is, so the thing was, they basically say that we will basically, boosting is basically a method, it's a popular machine learning technique which they actually used. It's not that they invented it. It was a method used in machine learning. It's basically a method to make weak classifiers a strong classifier. So the idea is basically given a set of data points. You basically learn a partition, which is just a weak classifier. So you use basically some simple feature, one of the two features, let us one of the n number of features, or one of the n number of filters are features that you are using. You use some filters. So you use one of the parameters to decide to partition your space from in your two classes. So in this case, for example, face class or non-face classes. Then now this is a weak classifier. This will want to learn everything properly. So for example, these two have been misclassified and this thread has been misclassified. So bot boosting says you reiterate it. But in the next iteration, you increase the weights of this misclassification of the previous weak classifier. So you increase the weight of these two and these two, and then try to learn another partition, which now this partition will be very careful to not misclassify these things because these will weight more in our loss function. So this will be, it has to be given more priority. So the next partition that it will probably tend to come somewhere here, which will not misclassify this, but it may misclassify some other things. For example, these two have been misclassified. So you go on iterating it again. So increase again the weights of these two again, and learn a third classifier, which actually does well on these modified weight samples. So now in that way, you will end up learning several of weak classifiers, which are good in partial sense, but they are not strong in avoiding all false positive and false negative. So what you do, you come up with a final classifier, which is just a linear combination of these weak classifiers. So you use these partitionings, these different partitions, and come up with a linear combination of these weak classifiers. So again, you can think in terms of a tree also. You are basically using these classifiers in a hierarchical fashion or maybe in a linear combination. So the idea is you come up with this kind of a more strong classifier by learning these three weak classifiers. You will be able to partition your n-dimensional space into different regions, and you will be able to predict more accurately. So this is the boosting method. And finally, the last thing that they basically proposed, which was very innovative, was using a cascade of classifiers. So instead of just using one strong classifier, they ended up using a combination of weak classifiers and a strong classifier in a hierarchical fashion, in a cascaded manner. So in the first stage, you will have some classifier. Normally it will be a weak classifier. In the next stage, you will have another classifier, and so on. The idea was again to boost your speed. The intuition here is, for example, if you're trying to detect a face, to detect a face, you will be generating many locations in your. You'll be testing at several locations in your images, and also at different scales. We'll be also scaling them up because face can be of different size. So you'll be coming up with many proposals, many locations which are proposed locations for faces, and you need to compute hard features on that and do a classification. Now, at every location, doing everything in a compute will be very compute intensive. So the idea was, some locations, for example, if you're looking at a sky region, which is just a plain background, you can learn it you can reject it very quickly that it is not going to be a face region. So you can use a very simple classifier to do that. Probably a very simple, just one hard feature to decide that that there is no face here. So that classifier can be very fast classifier. Maybe you will be using just one feature, and it will be throughout easy negative. So all non-faces, it will be very easily you will be able to discard them. Definitely, this is not a non-face. It may predict a possible region where there is not a face. It may predict that there is a possibility of face, but that is not a problem. So it will have a very low false positive. Let me see. Let me get the terminologies right. Again, I don't want to use the term false positive, false negative, because I want to explain it later on. But I'll say face and non-face. So it will very it will not make a mistake in saying non-face, but it may make a mistake in saying it is a face. But that is okay, because now we'll have a more rigorous examination later on. So in stage 2, we can use a more robust classifier, which can be not so fast, but still fast, but it will still throw out some of the false positives which were passed on from the stage 1. It will be able to reject all those non-faces, and it will pass more further to the further candidates to the next stage of the classifier. And this stage of the third stage, or whatever stage, you can use a more robust classifier which uses multiple R features to learn a more robust classifier, and which will throw out more hard negatives. And finally, you will have the output of this will probably be a more accurate probability, saying whenever this classifier says it is a face, probably this is going to be really a face there. So the idea with this cascading thing is that you for most of the regions, you very quickly reject them by using very weak classifier, which can be calculated very fast. But only regions where there are chances for faces, you do a more rigorous analysis and then do a prediction. So the result is you get a fast classifier, which is also at the same time very accurate. So these are some examples. I'll stop at this slide. So these are some examples of Euler-Jones face detection. As you can see here, it does quite good job with even very low resolution grayscale images. Normally, it doesn't use actually color information. It just uses the grayscale information of the things. There is some misprediction in this case here. For example, probably the pattern of the eyes and nose, it got confused with this football soccer, where it did not got confused with this one. It does miss some people, especially when there is a clutter and so on. Also, some people, probably the person with some mustache is not getting detected here, because that may be because in the training data set, you didn't had a lot of faces with mustache. Probably these were all Western faces where people did not most of the people did not have mustache. So probably that can be taken care of by including people's faces with mustaches also in your data sets. Also, this is an example from the original training from the OpenCV implementation function. It doesn't fare well on the side faces. Only generally this faces it detects well front-looking faces. But if face is from side looking, it does not well because again the same reason, because the data set that it uses doesn't has side facing profile. But that can also be very easily overcome if you add side looking faces in your data sets. Then it is not a problem for this method to learn that case. So it does work well and does work good with good reasonable accuracy and reasonable speed, even in low computations environment like embedded systems in embedded microprocessor in a camera or so on. This is a visualization of how the algorithm runs. It's a slow motion visualization of how this algorithm runs. So basically it uses, as we said, it uses a 24 by 24 window size at different locations. And at each location, it tries to, I don't know whether the captioning is visible, but you see some of the R features are being used. At some location, only 1 or 2 features are being used and it is very quickly discarding them. But at other locations where there is a chance of space, it is using more number of features, using a more at higher, going towards a higher stage of the cascading to detect whether there is a face or not. So some places it is doing very fast job. Other places where there is a push chance of face, it is running doing more rigorous computation. And the score, the prediction score, confidence score is also being shown in the text here, and the stage at which it is predicting here. So for this location, for example, at this location, if you see, it is going to do a more rigorous analysis because this is a location of face, and probably you are getting a very high 100% or very high percent accuracy here. So you mark those locations where you get a very high response as the possible candidates of faces. And you go on doing this for the entire image, and then again, it will run through the entire thing. but then again it will take a higher window and again resample it to 24 by 24, because as I said, faces can be of smaller or larger sizes. So it is going to now use a larger window size, but it will resample it to 24 by 24 and compute the features. So this thing will keep on doing for multiple scales as in different scale space, and will do region proposals for all those different locations. And wherever it finds higher probability, it will mark those things. And finally, it will end up doing a non-maximal suppression. Again, the same technique that we have seen. So it will do a non-maximum suppression. So within in the neighborhood, wherever it got a maximum response, it will just pick up that and prune the neighboring response. And in this case, finally, it will actually boil down to detecting a face in this region. So this is a higher, again another higher scale window. And finally, predicted just one window here because all other windows were just very neighboring to it and having a similar response. So